Just 1 second. So we were doing we were basically talking about why are transition metals why are they colored? Okay, that was what we were talking about. And before moving to that, we wanted to figure out. We had to do the basics, which is it had all to do with the d-subshell. And I was telling you that the d-subshell has 5 d-orbitals. All of them, they kind of look exactly the same, except that the orientation is different. So one of the d-subshell is between the x and y axis. Okay, so the electron is buzzing in these areas between the x and y axis. Another one, okay, this one is between the x and z axis. The electron is buzzing around between the x and z axis. So they all have different planes. So you've got ये वाला कौन सा? This is I think d yz. I mean this one over here. So that means the electron is buzzing in the yz plane. And the electron density is going to be between y and z axis. And then finally you had this one. This one was called dx square minus y square, or dx2 minus y2. The electron density over here is, again, it's in the xy plane, but the electron is on the x and y axis. Or the electron density, the two electrons are buzzing on the x and y axis. Okay, so the electron is buzzing in this area. And then finally you have the last one, which is called the dz squared. Okay, let me. So the last one actually looked kind of different compared to the other ones, because the last one kind of resembles, resembles the p orbital. It doesn't really have 4 lobes, so it's not your typical d orbital, but it's like a p orbital, except with one thing, and that one thing is that in the middle over here, there's going to be a donut-shaped area where there's going to be a very high electron density in this donut-shaped area over here. Let me. So there's a donut-shaped area in the middle, and that will also have a very high electron density. So I'm going to show you the. I'm going to try and show you the actual. Let me share the screen just 1 second. So this one, I'm going to show you the d-subshell. And the actual. Yeah, let's say this one. So I'm going to show you how the d-subshell looks like. The one with 4 lobes, that's your d-subshell. Okay, this is another d-subshell. Any of these with 4 lobes, that's this one is a d-subshell. So that shows the electron, basically the negative charge spread out in 4 different lobes. But it's going to have orientation, and let me show you what those orientations are going to look like. If I can have a, yeah, this one. So this one is like a really nice picture. So this kind of shows that the electron is buzzing in different areas. They're not overlapping. All of them are independent of each other. Like if you're standing over here in the middle and there's space around you, there's an electron in this one is in the YZ plane. You've got an electron in the XZ plane, an electron in the XY plane, an electron that's on the X and Y axis, and you've got an electron that's buzzing on the Z axis. So none of these regions, so you think of yourself standing in the middle and the electrons everywhere, except none of those electrons are overlapping with each other. So is this clear, the 5d orbitals of the d-subshell? You clear, Isaac? Is this clear, Rumesa?
Yes.
Yes.
Okay, so that is what your d-subshell is, and you'll be asked to draw this. When we do past papers, so then we'll see how we're going to do that. And just 1 second. As we're coming back to this, so you just have to draw rough sketches. Okay, now the screen is in front of you. As you just have to draw rough sketches of this. The important thing that you have to remember is that there are certain d orbitals in the d subshell. Each one can accommodate a maximum of 2 electrons. So there's certain d orbitals, and those d orbitals, the electron density lies between the axes. So the electron density over here is lying between the axes. Here, the one that I'm circling over here. The electron density over here in the dxz also lies between the axes. In dyz, the electron density also lies between the axes. In dx square minus y square, the electron density lies exactly on the axis. And in dz square, the electron density lies exactly on the axis. So if I write all those orbitals together, okay, so my d subshell, it's consisting of dxy, dxc, dyz, then there is dx2 minus y2, and then there is dz squared. Now these ones over here, the first three, in these ones, the electron density lies between the axes. And this thing is going to be very important. So it lies between the axes. And the last two, the x square minus y square and the dz square. In these ones, the electron density lies on the axis. Now you'll be asked to fill up these d subshell. So always remember that when you're filling up d subshells, it's important that the d subshell is going to be filled in a single manner first. Just like your p subshell, px, py, pz, it gets filled in a single manner first, and then it gets doubly filled. So in a very similar way, your d subshell gets filled in a single manner first. So it basically gets half filled first, and then electrons start pairing up. And orbitals become doubly filled. So for example, I've got, let's say I've got chromium, it's got, not chromium, if I've got titanium. Titanium, I think, is, scandium is 21, 22, 23. I think titanium is 23. So if I write down the electronic configuration of titanium, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Then it's going to be 4s2. The 4s subshell fills first. And then there's going to be electrons entering the d subshell. And in the case of titanium, this is 20. So there'll be 3 electrons. So 3 electrons going into the d subshell. How would the d subshell look like? Like if I have if these boxes represent the 5 d subshells, So how would 3 electrons enter the d subshell? It's going to get filled in a single manner first, while the rest of it is empty. So any subshell, just like a p subshell, it will be filled in a single manner first. एक और कर लेते हैं. If I have cobalt, iron, cobalt, nickel. So cobalt has 27 electrons, I think. So that's going to be, I mean, everything would be exactly the same. Then the 4s will get filled up, and then you will have 27 electrons in the D. So how would this look like? So this is going to look like it's going to look like 7 electrons, right? So it's going to be filled in a single manner first. So that's 5 electrons, and then it's got 7 electrons, so then the pairing will start. Okay, so that's how your D subshells are going to get filled up. Ye clear hai, Qasim, Isaac, Romessa? Is this clear?
Yes, sir.
Yeah.
Achha, so that's cobalt. Now, coming back to the D subshell, because remember, we have to focus on the colored compound thing. So remember, that's your D subshell. And also remember for a fact that the D is not involved in bonding. It's not doing anything. The D is actually, it's actually a subshell that's inside the atom. Uh, most of the time, if the electrons are lost, they're going to be lost from the outermost shell. But anyway, so we're going to start talking about colored compounds and colored complexes now. So for example, I've got copper with ammonia in it, and that's deep blue in color. So I've got CuNH3 and it's got a +2 charge, and it's a deep blue solution. Now this one is an octahedral complex, which means that it's making, I mean, there are 6 NH3s. That indicates that there would be 6 bonds, and all of them would be 90 degrees to each other, and that's called an octahedral complex. So I'm going to draw just that. So I've got copper in the middle, and copper has, this is my z-axis, and that's my x-axis, and this over here is my y-axis. You can think of this in 3 dimensions. So I've got x, y, and z-axis. And remember, copper at the moment is bonded to NH3. So you got NH3s. There's copper +2, and it's getting surrounded by NH3 ammonia ligands from all sides. The ammonia are getting attracted to the copper, which is +2. Okay, so I've got lone pairs. And those lone pairs are getting attracted to copper +2. Now remember, we're dealing with copper +2, which means copper has lost, so copper is argon, and then it was, the original copper was 3d10 4s1, but it's going to lose its outer electrons. The s is going to go, and there's going to be 1 electron leaving the 3d as well. So there are 9 electrons in the 3d at the moment. So while the ammonia molecules are getting attracted to this copper +2, then you have to, what you need to imagine is that the copper ion in the middle, that's the electronic configuration of this copper ion. It's got a d subshell, and it's got 9 electrons in it. So what's going on is that I'm going to draw these 9 electrons. There would be some on the axis. Do you remember? Look at the d subshell. There are 5 d orbitals, And in those 5d orbitals, there would be electrons that would be buzzing on the axis. So there were orbitals that were lying on the axis, right? So think of the d-subshell over here. It's got 9 electrons, and ammonia is on the outside. Okay, so remember, if I go back and show you the d-subshell, there were electrons that were on the axis. Okay, like the 3d x2 minus y2, or the z square. I mean, they had electrons on the axis. And the other ones, they had electrons between the axes. So there are areas around so there would be electrons that would be buzzing between the x and y axis, x and z axis. So there would be electrons, the 9 electrons of the d subshell that would be buzzing between the axes. Okay, so is this clear? Is this visual representation clear? That this is how the d subshell, all of them put together, would look like. Ye clear? Is this clear? Qasim,
Oh,
clear? Isaac, is this
yes.
clear? Hmm?
Yes.
I'm just saying that individually, this is what the d subshell looks like. Uh, the d has 5 orbitals. 3 of them, the electrons lie between the axes. So between the x and y axis, right? The electron could lie between the x and y axis. The electron could lie between the x and z axis, right? The electron density could lie between the y and z axis in these areas. Or you have 2 of them, the electron density lies exactly on the axis. X square minus y square, the electrons lie exactly on the axis. 3d z square, the electrons lie on the axis, including the donut-shaped area over here. So the point I'm trying to make is, imagine or visualize all the d orbitals together. So copper ions, which are in the middle, think of this as the copper ion, which is +2, and it is attracting all the ammonia ligands. The copper ions have 3d and it's got 9 electrons in it. So there would be some electrons in the d subshell that will be on the axis, whether it's the 3d z square or the 3d x square minus y square. And there would be plenty of orbitals or electrons that would be lying between the axis. Okay, so 3d9 would, all together, these 9 electrons would kind of look like this. Okay, Romesa, is this clear?
Yes, sir.
Okay, so now the thing with the 3D subshell is that they were degenerate. So 3D subshell uh, has degenerate orbitals when isolated. In an isolated environment, it's got degenerate orbitals. What is degenerate? Degenerate means all of them are identical. So that indicates they have the same energy level and type as well. I mean, for example, there's no difference between the PX, PY, and PZ. The only difference is that the orientation is different. In one case, the electron is on the x-axis, on the other case, the electron is on the y-axis. So the 3D subshell is degenerate, which means all of them have exactly the same energy level. So if I get 3 to 5. So if I draw them, the 9 electrons, right? Remember, I'm drawing 9 electrons. I'm talking about copper at the moment. All the orbitals are exactly identical. EK except 9 electrons, right? So this is the energy level. They all have exactly the same energy level. Acha, lekin, what happens is, so why do they get colored? So what happens is, when they form a complex, take it the way you see it on the screen. Imagine ammonia wasn't there initially. So all these ammonia ligands, they were not attached to the copper. So all the d orbitals and the 9 electrons that were buzzing around the copper, but they had kind of the same energy level. But then this copper plus 2, remember this is copper plus 2. Then what happened is that it started attracting these ligands and their lone pairs. So all these ammonia ligands, they approach the copper ion, they get attracted to it. They're not going to go very close to it because the D is going to have a lot of electrons and it's going to repel it. But the copper plus 2 charge, the ion has an overall charge because it has lost the outer electrons. All these ligands are getting attracted to the copper in the middle. Now, what that does is that it creates repulsion. So what happens is that the lone pair, remember this lone pair over here, it's going to exert some repulsion on this particular d orbital. You got another lone pair and it's also going to exert a particular repulsion on this d orbital, which is on the axis. So all these on the axis, they're going to start, they will start getting repelled by the lone pairs. While the middle ones, you get the ones that are between the axes, they're not going to be repelled as much. Now, so an important point is that lone pairs on ligands exert repulsion on specific d orbitals that lie on the axis. So is this point clear, this minor point, that when it's forming an octahedral complex, the ligand approaches, gets attracted to the copper ions, and the ligand lone pairs will exert a repulsion on the d orbital, which is on the axis. Is this clear? Rumesa, Isaac, Qasim, is this clear, this part?
Yes, sir.
Yes.
So now what happens is that originally your d orbitals were all exactly the same, but they are no longer going to be the same. There would be some d orbitals that would have to face a lot of repulsion, and there would be some d orbitals where it's easier to keep electrons. Like the orange ones over here, they don't face direct repulsion. Okay, let it come on the screen. So the orange ones over here, these ones, I mean, they're not facing direct repulsion. So it's kind of easier to keep electrons over here. And it's much more difficult to keep electrons in the green ones. So going back, keeping electrons on the axis, that becomes difficult. And keeping electrons between the axes, that kind of becomes easy when it's forming an octahedral complex. Okay, so easier to keep electrons. And over here, difficult to keep electrons on the axis. So your D subshell kind of splits. So is this idea clear that your D subshell is splitting? You clear, Saroko, Isaac, Qasim, Rumesa, is this clear?
Yes.
Okay, so again, just have a look at the D subshell. All of them were identical initially before the ligands approached. And the ligands created repulsion. So in the green orbitals over here, it became really hard to keep electrons. And in the orange ones, it became easier to keep electrons. So your entire D subshell split into two. There's a place where it's easier to keep electrons, sorry, difficult to keep electrons. And between the axes, there's a place that's where it's easy to keep electrons. And that creates an energy gap between the, so it creates an energy gap between the two sets of orbitals. So originally there was no energy gap, but now they have an energy gap, which is delta E. And remember, copper had 9 electrons, which meant that they were the D, the entire D subshell was had some space in it. 9 electrons meant that all these orbitals had were full except for one of them, right? It had 1 electron. Now, what can happen is, and this is where colored compounds come in. Now, what actually happens is that electrons from the lower d subshell or the lower energy d orbitals, they tend to jump from the lower to the higher one because there's space available. So they can kind of jump around. So if there's an electron which is over here, between the axes, it might jump from there and it might switch to on the axis. But for that, it would have to face a lot of repulsion and it would have to be really energetic. So, so electrons from low energy d orbitals, they gain energy and move to higher energy d orbitals. But to jump from lower energy to higher energy, they need some sort of energy to be absorbed, and they do that by absorbing frequencies that belong to the visible light. Basically, what happens is that the energy that any electron or quantum particle is absorbing, energy is always proportional to frequency. Now you've got a lot of frequencies around you. You've got the visible spectrum is like really, really tiny. Like if I show you the visible spectrum, there's nothing special about transition metal complexes because in every atom the electrons can jump around. They can move from the lower energy to the higher energy. So let me show you that. Okay, there was electromagnetic spectrum, right? I mean, you must be already familiar with this. Okay, now the point is that the visible spectrum is like huge. No, the visible spectrum is like really tiny. It's just the middle rainbow that you see over there. Eager, violet, indigo, blue, green, yellow, orange. The photons and the energy spectrum is huge. You start off from radio waves and you go all the way till gamma rays. Gamma rays are high frequency, radio waves are low frequency. So the point is, electrons in any atom can gain photons or can absorb frequencies and gain energy and they can move to higher energy. Except for the fact that this difference over here specifically matches frequencies that belong to the visible spectrum. Like if an electron wants a lot of energy, it would probably gain that energy from very, very high frequency waves like gamma rays. If an electron needs very less energy to jump around and go into excited state, might absorb that from radio waves. But in transition metals and their complexes, the energy gap that is created that exactly fits the frequencies that belong to the visible spectrum. So delta E matches frequencies that belong to the visible spectrum. So there's nothing wrong with sodium. Sodium's electrons are also jumping around, but they're absorbing frequencies that either are too high or too low, which is why if sodium absorbs an electron or a photon or a frequency from light, you're not going to notice anything. You're not going to like if radio waves go missing, you don't even see radio waves. I mean, the mobile waves that your mobile is emitting, you're never actually able to see it. So which is why you never see colors in sodium because it's not absorbing any of the colors. But in the case of transition metals, the energy gap matches frequency that belongs to visible spectrum, which is why you always see a complementary color. So, for example, if the metal complex absorbs, if a metal complex its electrons go into excited state and it absorbs yellow light, then you wouldn't be able to see yellow light. So you're going to see all the lights except for yellow light because that's going to be missing. Those photons, those frequencies are going to be missing. If in a transition metal complex, electrons are going into excited state and they're absorbing red frequency, this energy gap matches frequencies in the red spectrum. So what will happen is you're not going to see red. You're going to see all the other colors except for red, which is why what you'll end up seeing is the complementary color. So if the complex absorbs red light, you don't see red light. You see all the other colors. You see blue, you see yellow, you see green, but you don't see red. So always a complementary color is seen. Because this is basically the idea of why transition metal complexes are colored. I'm going to write a formal answer for this. But is this point clear? Isaac, Qasim, Rumesa, is this clear why are transition metal complexes colored?
Yes.
Okay, so I'm just going to quickly summarize. You had a d-subshell. The d-subshell, all the electrons were exactly the same. I mean, they had exactly the same energy level. The ligands came in, they formed a complex, but the ligands, because they were attacking on the axis, so it became harder to keep electrons in the d-subshell, especially on the axis. So your d-orbitals, they split up. There were some d-orbitals where it was easy to keep electrons. There were some d-orbitals where it was harder to keep electrons. And there was an energy gap between the two. And electrons could jump around. They could switch from the orange ones over here to the green space over there. But to go to the higher energy orbital where there's more repulsion from ligands, the electron has to be more energetic. So it has to absorb some frequency, and that frequency comes from or matches frequencies that belong to the visible spectrum. And therefore you see a complementary color. Okay, so tomorrow we'll continue with this, and I'll write a formal answer of how you're going to answer this in the exam. Okay? So, everyone. Take care, Allah Hafiz.